Hello, everyone. I hope you had a good lunch. Thank you all for being here. I'd like to first start off by introducing my co-authors here. The first name is my PhD student there, Benjamin Abu. Then we have Rahul Reddy Chenareddy. He's a PhD completed and working in the industry now. That's the third person is me, and the fourth person is Mahmoodra Dattaha, who is a professor at the University of New Mexico, and also happens to be my advisor too. So I'd like to start off by introducing his team first. Now, you've noticed the pictures on the first slide. You've noticed the pictures on the second slide here. So that's me. Oh, how amazing it is to be young. That's Dr. Rahul Reddy Chenareddy there. He happens to be my husband as well. We love to work so much that we ended up getting married. That's our amazing advisor there, our academic father, Dr. Mahmoodra Dattaha. I am now an assistant professor at the University of Oklahoma, and this is my team there. These are the team of 8 undergraduate students and 3 graduate students. We're very heavily involved in fiber reinforced polymers for structural materials and engineering and design. 3D printed FRP, polymeric concretes, comparisons with asphalt and cementitious concretes, and 3D printing with cementitious concrete. This particular work is very interesting, and I'd like to start off by the motivation that enables us to talk about this topic here. We have aging pipe infrastructure that serves as a huge problem, especially that leads to catastrophic failures and cascading our infrastructure damage. The pictures that you see are actually provided to us by the Oklahoma Department of Transportation. This is a failure of a corrugated metal pipe. Corrugated metal pipe, if you're not aware, they're basically just corrugations inside metal pipes. This failure of the CMP led to a slope wall failure in Okmulgee County in Oklahoma, and it was more of a reactive repair that led to more than $1 million of an emergency bid. And this emergency bridge repair sort of gives us an idea that we address these aging infrastructure problems sometimes more of a reactive sort of a system rather than proactive. And clearly there is a need for resilient, reliable infrastructure, but how can we think about those things in terms of design is a real big problem. So corrosion-driven CMP failures are costly and catastrophic, highlighting the need for durable retrofit solutions. Now, Arizona DOT took up this particular emergency repair, again, a reactive sort of a repair. This is a sewer line through a storm drain. It's 300 foot long. It's a 36 inches water pipeline. And it was easier to do a wet layup with carbon fabric than anything else. So they had to close down the entire system for about a full day. It was designed by Dr. Chenareddy. And the fact that Arizona DOT opened up to get this particular repair done, and it shows that the industry is more and more open to using fiber reinforced polymer composites and polymer related materials in these emergency situations. It brings also to one of the other repair strategies that are predominant in the pipe infrastructure repair and retrofit. They're called conventional lining systems. Now, what lining systems are, and the reason I'm giving a background is maybe there's some people in the crowd who don't know this, and it helps me go into the research topic. So bear with me. Non-metallic liners, well, metallic liners as well, but non-metallic liners are used in these existing pipe infrastructure systems, which are pretty much well corroded or close to aging in terms of not being able to carry on the loads anymore. So these liners are used inside the systems, pipes, existing pipes, instead of open cut, dig, and replace. Because open cut, dig, and replace, if you're looking at just strictly numbers, a 24-inch diameter, 72-foot long culvert is associated with a $41,000 cost, whereas a slip lining process with in-place retrofit with the same sort of pipe system, we're showing here high-density polyethylene liners, HDPE. We're talking about $18,000 of cost associated with that sort of a repair. So HDPE is one of the non-metallic sort of liner systems that are used for these repairs, and they improve durability, they improve the capability of these infrastructure systems to go on. There's metal pipe liners as well that are used, but non-metallic liners are more predominant just because of the fact that how many times in their age and service do you have to go back and replace or repair them. So considering these liner systems, if you look at the liner itself, they're placed into this existing culvert structure. You create a certain annulus here, which is filled up with sort of grout systems. They can be cementitious grouts, polymeric grouts. Unfortunately, with HDP, we have a lot of abundant data available as to how the mechanics works and how the durability and structural performance works. More importantly, how does the load transfer work between the CMP and the grout and to the HDPE liner? If you consider newer materials like glass fiber reinforced polymers to get these slip liners into the culverts, there's a lot less information available on how this entire system acts as a composite. So how does composite action work? So we've come up with this holistic mechanistic understanding between two institutions, University of New Mexico and University of Oklahoma, to be able to understand these systems better in terms of repaired or retrofitted with glass fiber reinforced polymers. So the first thrust of this mechanistic understanding involves flexural and more of a global composite behavior, including a life cycle cost analysis. And the second thrust involves more of a localized load transfer and sort of a circumferential behavior and response understanding. So what we aim to establish with this multi-institutional collaboration is how composite liner grout pipe systems govern structural performance and long-term efficiency. So I'd like to get into some details of these experiments. I'm happy to provide you the journal papers that have been published in these aspects because that's where truly you will find more details if you're interested. So talking about thrust one, which is that flexural response that we were studying, and this is primarily Dr. Channareddy's dissertation. We see a GFRP slip liner system here, and the bottom picture is of a corrugated metal pipe. Basically, you have the slip liner going into the corrugated metal pipe. Each of these materials were evaluated for their own properties and mechanical performance. There on the bottom, you have the grout. A polymeric grout, two-component, was used for this particular project, which brings to our actual aging problem or the corrugation-induced failure problem. So this damage was created in the CMPs using an accelerated corrosion, very fast 20-day electrochemical cells. So you can clearly see the effect of corrosion after and compare it to the before picture, including interior corrosion developed with sort of a spraying effect, increasing oxygen levels inside. And you have this entire system now corroded. So you have an uncorroded system and a corroded system for comparison. The corrosion that was managed to be achieved was about 4% lowest and 29% maximum in the middle center areas. After surface preparation of these GFRP slip liners, the slip lining technique was conducted, where here you can see this corroded metal pipe with the slip liner system inside, and the grout filling is being carried on. So pumping of the grout is being carried on to make this sort of a composite system. Full-scale structural tests were conducted. Sorry about that. Full-scale structural tests were conducted. So under bending, these full-length pipes were investigated and load deflections were observed. There was an initial separation of the corrugated joint. Then we had GFRP matrix damage. Then we saw some GFRP failure as well. Now, these are tested to failure. So you're looking at an overall response here. Then you also see some of this seam joint, lock seam joint separation, the corrugated steel pipe joint completely separated at the end of the test. So overall, if you look at the results of a non-corroded and the corroded, we do see some good composite action being held and carried forward till the end of the test in both systems. And the corroded one, though there's damage to the steel pipe, you don't see too much of a deterioration in terms of load carrying capacity. A finite element model was also created, which agreed well with the experimental results as well. So again, an in-depth study can be found online in the journal paper and the dissertation. The thrust too, which comes to the localized and circumferential behavior, we're looking at now more of the slices of these pipes and liners. You're looking at a GFRP slip liner, exactly the same that you've seen already, and then you have the CMP. Now you're looking at slices here rather than this full pipe that you saw in the last thrust. The additional element we sort of interrogated in this particular project was including with this polymeric grout, we also studied the cementitious grout and the comparisons with the bond-related abilities. If you see the top 3 pictures there, that's the cementitious grout. Filled in, the grout annuli was completely occupied and cured with a wet burlap. That is pretty much, well, not in the industry, sometimes maybe a curing agent, but 28 days of curing is highly unlikely, but we've tried our best to represent more of a laboratory and high quality control. The last 2 pictures that you see here on the bottom are the polymeric concrete that was mixed and the annuli completely filled with that, room temperature cured. And this is the test setup that we conducted with a 2-point bending and having an LVDT in the vertical and horizontal to sort of get this effect of how the deflection is in the slip liner and the overall composite pipe in the horizontal and the vertical directions. So if you look at these results here, you see that the vertical and the horizontal displacements for the corroded and the uncorroded, the comparisons. The beauty about the polymer concrete that enabled actually sort of a fiber bridging option. So you can actually see those fibers really being engaged in this testing until failure. In the cementitious concrete, on the other hand, you absolutely see a complete detachment of the grout from the GFRP slip liner itself. So you see these clear differences between these 2 grouts where polymeric concrete is able to engage those glass fibers in the GFRP slip liner, whereas a cementitious grout is unable to get that efficient load transfer possible. So this is a very key observation from our study. And you also look at the possibility of energy dissipation in the polymer concrete grout, which are those top 2 curves here, whether corroded, whether uncorroded. You do see in the red line a sort of a reduced load capacity with the corroded, not being offered with as comparable as the uncorroded, but still you have that energy dissipation and being carried forward into the ultimate deflections that you see. Through this study, it's also important to sort of understand what HDPE liners, GFRP slip liners, and just the CMP itself as slip liners can do to these systems for a composite action in terms of rehabilitation and maintenance events. So each arrow that you see there is one of those events, and you see for CMPs, which are primarily corrosion-driven failures, you see many of those replacements, retrofit, replacement, sort of a cycle that happens. And HDPE, which is still moderate performance but non-structural in its essence, you see more of the replacement not happening too many times as the CMP. GFRP pretty comparable, but what we've seen in these results is structurally, based on the grout system that is used in the annulus, you have more of a structural contribution from these liners. If you see a 50-year life cycle cost versus a 100-year life cycle cost, yes, initially the cost is high to enable a GFRP slip liner and polymer concrete, but if you look at the 100-year life cycle cost, you have those costs very much drop down for GFRP rather than comparison to HDPE or CMPs. So I'd like to conclude this talk with just very crisp conclusions here, just 5 of them. We've seen that across independent studies, GFRP-based culvert retrofit consistently demonstrates a shift from repair-based strategies to performance-driven and durable infrastructure solutions. GFRP slip lining enables structural, not just a protective retrofit, so achieving that composite action and enhanced load capacity enables us to conclude that. The durability is governed by corrosion resistance and interface mechanics. You've seen that those cementitious grout basically completely debonds from that GFRP slip liner, where polymer concrete is able to truly engage that high-strength glass fiber. Grout selection is a first-order design parameter with polymeric systems, increasing stiffness and improving load transfer. You've seen about 7 times an enhancement. And service life extension, which is up to 7,500 years, reduces the intervention frequency. So you reduce those possibilities of going back and replacing or repairing these systems with such non-metallic materials. And if you've looked at the life cycle performance, remembering that not initial cost governs the solution efficiency with GFRP systems, demonstrating the lowest long-term cost instead of comparing to the initial cost. So these 2 projects have been funded by the Transset and the Accelerated Bridge Construction agencies. So I'd like to acknowledge both those agencies, and I'd like you all to thank you all for your time. So any questions, happy to take them.